Today we're going to talk about absolute extrema. We're going to start this by talking about an extreme value theorem. This states that a function f that is continuous on a closed interval from a to b will have both an absolute maximum and an absolute minimum on the interval. So the important thing there is that you have a continuous function and it's continuous specifically on a closed interval. So here, let's look at this example. Okay, we're looking at the graph to the right, and it asks us to determine the absolute extrema for this graph. So basically here, absolute extrema is going to be that there is a point higher than any other point on the graph, or there is a point lower than any other point on the graph. And so on this one, if they're asking for an absolute max, then we want to look at the graph. Notice that the extreme value theorem in this particular situation guarantees both a max and a min. We see that we have a nice continuous smooth function on the closed interval. It looks like it starts somewhere between -3 and -2 all the way over to +3, and we notice those two endpoints are included. So if we're looking for the absolute highest point, then we can look here and we can see that our graph doesn't go any higher than it looks like +16. So we're going to say we have an absolute max of y equals 16 at x equals, and we want to do the x values for those. Looks like at -2 and at +2. So we'll say x equals -2 and +2. All right, absolute minimum, the same idea there. We want to say, is there a point lower than any other point on the graph? And on this particular one, it looks like we can come through here, and it looks like we have a low point somewhere between -8 and -12. We can see on this particular graph that our y-axis is scaled by 4s. So it goes from 0 to -4 to -8 to -12. So it looks like, and on this one, we'd have to make sure on the test that we were certain on this. And on a test, I would make sure also to make this clear as far as, exactly where is this. It looks like it's about halfway between -8 and -12, which would mean it would be at -10. And so like I say on a test, I would make that more obvious to you. So on this, we're going to say we have an absolute minimum of y equals -10, and that occurs specifically at what x value? So it looks like it occurs at x equals 3. All right, so when a question asks for absolute extrema, it's meaning what is the absolute highest point that's higher than any other point on the graph, and what's the absolute lowest point that's lower than any point on the graph. And also remember that when we talk about max or mins, we're always talking about a y value. So make sure your answer is in the form y equals, and then also we specify at which x values does it occur in case there's multiple x's. All right. The next example, it wants us to draw a graph of a function that's continuous on the open interval from 0 to 5, but that does not have any absolute extrema. Basically, this question is so that we understand the extreme value theorem, in that not only must you have continuity, but you also must have a closed interval, and we're able to see from this example why the interval cannot be opened. So on this one, students could give me, I'm going to say, various different answers, but the big thing here is that you have an open point at 0. So let's say on this one I have a graph that started here, but I'm going to make that point open. It's going to be continuous, and then I'm going to have it, let's say, end over here somewhere. And in here, what I'm going to do is make sure to stay between, let's say this was going to be my, quote, lowest point, but it can't be since it's open. I'm going to make sure it's the lowest and that I don't go any higher than this point over here. So that makes sure that I don't have a absolute maximum anywhere. So where would have been my absolute max or my absolute min if I put open circles at those particular locations, then it guarantees I don't have an extrema as long as I haven't gone any higher or any lower than those open ordered pairs. So on here, we notice that the function is continuous from 0 to 5, but because I haven't gone any higher or any lower than my open points, then it doesn't have absolute extrema. All right, now what I want to do is look at a polynomial and go through the process of finding absolute extrema if you're not given a graph. The first step is you're going to find all the critical numbers on the open interval of the interval they've given. So on these kind of questions, they're going to have to give you the function, and then they're also going to have to give you an interval of some kind. Make sure that you don't consider any kind of critical numbers that are not in the interval. So every now and then we can go through and find critical numbers, but they're actually not contained in the interval. We're not going to consider those. And then we're also not going to consider, I'm going to say, the endpoints as possible critical numbers. So let's go through and do that first for this first example. So it's asked me to find all absolute extrema. We've been given the function. To find the critical numbers, I first want to take the derivative of that function. So here the derivative would be 3x squared, and then minus 12x, and then plus 9. All right, to find critical numbers, this is a polynomial function, so I'd be finding where the derivative was equal to 0 to find those critical numbers. Usually also we ask and say to find critical numbers, we find out where the function is undefined, but that doesn't do anything in this particular case since we're dealing with a polynomial function. All right, so setting this equal to 0. It looks like there's a 3 that we can factor out of all terms. And then from here, I'm going to check and see if this can factor. If this factors, that's great. If not, you can always use quadratic formula. Looks like here I can use a -3 and a -1. That would multiply to the +3 at the end, but add to the -4 in the middle. And then we set each of these factors equal to 0. We notice over here that because that does not have an x with it, it doesn't make sense to set that equal to 0. Here, setting this equal to 0, we're going to get x is equal to 3. We notice that is not in the interval. So 3 is not an element of the open interval. We notice up here we're looking at a closed interval. The critical numbers must be in the open interval. So 0 to 2, but not including 0 and 2. So we notice that the x equals 3 is not an element of the open interval from 0 to 2, so that's not going to be included. And then we're going to come over here and we get x minus 1 equal to 0. We have x is equal to 1. We notice that is an element of the open interval from 0 to 2. Okay, so that's the only critical number that we're going to consider. Just remember from, I'm going to say notationally speaking, when we write this symbol, this means element. When we put a slash through it, it means not an element. So over here, this would mean element since it doesn't have the slash in it. That's just good notation for showing that something is in an interval or not in an interval. All right, and then from here, we're going to go to the next step. So we've done step number 1, essentially. Step number 2 is to evaluate the original function at the critical numbers that are within the open interval, and then also at the endpoints. Okay, so we have to make sure, underline that. That's something that's sometimes forgotten. So if you have extrema, absolute or extrema are going to either happen at the endpoints or they're going to happen at the critical numbers. So step number 2, we're going to go and take the original function. So at this point, we're trying to find highs and lows and evaluate them. I'm going to start at the first value in my open interval, or my closed interval at this point. The first value in the closed interval is 0. So I'm going to evaluate the function at 0. Okay, at this point, you can use the calculator. This one's simple because I'm evaluating at 0, but I'm not wanting you to spend a whole lot of time evaluating these values. This one, you get -8. All right, f of, and then what I'm going to do next is go to my next critical number. I usually do these in order. It's just easy for me to do. So on this one, we have x is equal to 1 is the critical number. So we're going to evaluate at f of 1. Okay, and like I said, at this point, I'm just going to plug that in my calculator to see what value I get. On this one, I get -4. And then finally, we're going to evaluate at the other endpoint. So we evaluated at 0 already. We're going to evaluate now at 2. All right, and evaluating there, plugging in the calculator, you're going to get -6. All right, as the last step, it says the largest output is the absolute maximum, the smallest output is the absolute minimum. So the last thing that we really have to do is just make a statement of our answers. So at this point, we're going to see which one's largest, which one's smallest. We see that this value right here is actually the largest. And we see this value right here is actually the smallest. And so we have our absolute max and absolute min. So we're going to say we have an absolute max of, and remember it's always a y equals, so y equals -4 at, that occurred at x is 1. So there's one of my answers. And then we have an absolute min of y equals -8 at, and that one we got from an endpoint we evaluated at x equals 0. Okay, so we've got the statement of our answers there in the last step. All right, so on here, what I want you to know is as far as finding absolute extreme is concerned, it's a relatively simple process as long as I'm able to find critical numbers easily. So you first find all the critical numbers. You make sure that the critical numbers you're considering are in the open interval. They've got to give you an interval to start. And then as your second step, you evaluate your function at the endpoints of your interval, and then also at the critical numbers that happened in the interval. The largest value is your answer for your absolute max, and your smallest value is your answer for your absolute min. So it's a relatively simple process. It should make sense to you here. All right, so now let's go on and look at, I'm going to say kind of maybe a more complicated problem as far as finding critical numbers is concerned. So this particular example, we see that we have a function that we're going to have to use a chain rule on when I take a derivative. Let's go ahead and take a derivative to start. So here I'm going to multiply that 1/3 out to the front. We have the x squared minus 4 that's going to remain on the inside. I'm going to reduce the 1/3 by 1. So 1/3 minus 1 is going to be -2/3. And then we're going to chain on the derivative of the inside part. So that would be times 2x. All right, now what I'm going to do is simplify this result. I'm going to get the negatives out of the exponent. And so on here, what I'm going to do is a couple of things. The 2x that I have at the end would be multiplied by the 1 that's up here in the numerator of that fraction. So 2x times 1 would just be 2x. That's going to be in the numerator. The 3 I have from the 1/3, it's going to be in the denominator. And then the x squared minus 4 all to the -2/3 is going to drop to the bottom and become x squared minus 4 to the +2/3. So that takes care of any kind of negative exponents. And then the other thing I'm going to do is set this up so that it's easy for me to, I'm going to say find critical numbers for. So notice that the x squared minus 4 on the inside of the 2/3 power actually factors. So we're going to write this as 2x over 3, and then I'm going to put this in brackets and say this is going to be x plus 2 and x minus 2, all raised to the 2/3. And in that way, it's just easier to find critical numbers for that. All right, so for the critical numbers, I find either where the derivative is equal to 0, which in the case of a fraction, that would be where the top is equal to 0. Or I'm going to find where the derivative is undefined, which in the case of a fraction is going to be where the bottom is 0. Now, the 3 that's in the front of the denominator is not relevant because it doesn't have an x with it. The 2/3 is not relevant because I'm going to be able to set just the factors on the inside equal to 0. So that will be where either x plus 2 is 0 or where x minus 2 is equal to 0. All right, so solving each of those, this one I'm dividing by 2, I get x equals to 0. All right, remember on this one, the interval that they gave us to begin with, it was a closed interval from -2 to 3, 0's in there, so that one I'm going to want to consider. This one, if I solve, this is x equals -2. That's actually an end point, so I don't want to consider that one. And then this one, if I solve, this is going to be x equals 2. That one is an element of the open interval. So this one's an element of the open interval from -2 to 3. So we're going to consider that. This one was not an element of the open interval from -2 to 3 because it was actually an endpoint. And this one over here is an element of the open interval from -2 to 3. All right, so that takes care of my first step, which was finding critical numbers. My second step is now going to be to evaluate my original function at the critical numbers that are in the interval and at the endpoints. So I'm going to start it out by saying f of, I'm going to evaluate at -2 first. And then I'm going to say this is, be careful with the sign, so it'd be -2 all squared minus 4, and then all that is raised to the 1/3 power. Notice here that -2 is going to end up being 4, so you're really going to end up with 4 minus 4 to the 1/3. 4 minus 4 is 0, so this whole thing is going to be 0. You can also just evaluate that on your calculator. All right, next thing we're going to evaluate at the critical number I found within the open interval, so that'll be f of 0. Okay, f of 0 is going to be 0 squared minus 4 to the 1/3. That's going to be -4 to the 1/3. Now, a 1/3 is the same thing as a cube root power, so that's actually something that we can do. I'm going to do that on the calculator. We're going to get approximately -1.587 and some more. All right, I'm now going to evaluate at the last endpoint, which was f of 3. I'm going to have to do that on the calculator. 3 squared minus 4 all to the 1/3. If you plug that in your calculator, you're going to get approximately 1.70975 and some more. Okay, and what we can do, like on a test, I'll let you know how many decimals I want you to round to online. You can obviously round to however many they say to do there. All right, so now as the last step, we're going to go and say that the largest of those values is my absolute maximum, and the smallest of those values is my absolute minimum. Okay, so let's say here, let's round to the nearest tenth. So we're going to say that the absolute max, we're going to be looking for the largest number. Okay, so it's y equals. The largest number I have over here, we have 0, it's definitely positive, but the 1.7099 is larger. So what we're going to do there, if we round to the nearest tenth, it'd be y equals 1.7 at x equals, and that was 3. And then we're going to have absolute min. That we're looking for the smallest, y equals, and I believe one of the values we got a negative on, that was when we evaluated at 0, we got the negative 1.587. If we round that to the nearest tenth, it'd be -1.6 at x equals 0. So we've got the absolute max and the absolute min for that problem. And like I say on the rounding, I'll let you know on an exam what I'd like you to round to. All right. So now let's go and look at a rational function and see there what we can do about finding absolute max and mins. Okay, on this particular one, let's first find the derivative. So f prime of x, we know we're going to be doing quotient rule here. So we keep the bottom, take the derivative of the top, and then minus, we're going to keep the top, take the derivative of the bottom. And it would all be over the bottom squared. So there's the derivative. We want to go ahead and simplify this out. We notice here that the times 1 is not going to change anything for the first group of stuff, so this is just going to be an x squared plus a 1. Be careful on the second group of stuff. We actually have this negative that needs to be run through, as well as a 2x. So what I'm going to do is I'm going to think about it as multiplying a negative 2x throughout that group. So that's going to give me a negative 2x squared, and then it's going to give me a positive 2x. All right, and then all of that, we're just going to leave the bottom alone. It's the x squared plus 1 all squared. All right, then go ahead and combine like terms. We have a x squared minus a 2x squared, so that'd be a minus x squared. I'm going to go ahead and put this in order. We have a 2x next, and then we have a plus 1. And then still over the bottom group squared. All right, and then from here, we want to go and find critical numbers. And so on this particular one, critical numbers, we're going to find from saying where is the derivative 0. That's going to be where the top part is 0. Or where is the derivative undefined? That's going to be where the bottom portion is 0. We can ignore the square on the outside and just set the x squared plus 1 equal to 0. All right, I'm actually going to do the x squared plus 1 equal to 0 first. On that one, if we subtract over the 1, it's going to be x squared is negative 1. If we then take a square root of both sides, we're going to get that x is a non-real number because we're taking the square root of a negative there. So we don't get anything as far as critical numbers from that group. Okay, over here, I'm going to factor a negative out. So that would be an x squared minus a 2x minus a 1 equals 0. And then when I try to factor that, I can't find factors of negative 1 that would add and subtract to negative 2. And so in this one, what we're going to end up having to do is we're going to have to use quadratic formula. And so on here, quadratic formula. The negative that I factored out, I don't need to worry about. So really what I'm going to do is worry about these 3 terms on the inside. Remember that quadratic formula, you use a's, b's, and c's as the values that are in front of x squared, in front of x, and then your constant value. So the value in front of your x squared term is 1. The value in front of your x term is negative 2. And then the value that's just your constant term is negative 1. All right, I'm going to take this work over here on the side. I'm going to remind you first of quadratic formula. That is, if you have a quadratic in the correct format, meaning that you have, I'm going to say everything in order from largest power to smallest power, you have the function equal to 0, then x equals, and the formula is negative b plus and minus square root is b squared minus 4ac, and then all over 2a. And we're using the a's and b's and c's that we've written down in the prior step. So be careful here. It's a negative and negative 2, and then plus and minus square root would be negative 2 all squared minus 4 times 1 times negative 1, and then all over 2 times 1. The negative 2 would make it positive 2, plus and minus. The thing you square will always end up positive, so that would end up being 4. And then we have a negative 4 times a 1, that'd be negative 4, and then that negative 4 times negative 1 would be positive 4. All right, and then at this point, we're just trying to get it down to the point where we could plug in a calculator. And so we're, I'm going to say kind of here at this particular point. For this particular question, plugging in your calculator, you're going to do 2 things. You're going to do parentheses around the top so that that whole group gets divided by the 2 that you have in the bottom. You're going to do one piece on your calculator with a plus and one piece with a minus. So you're basically going to type in 2 plus square root of 8, divide by 2 to get one of your answers, and then you're going to do 2 minus square root of 8 all over 2 to get the other answer. Okay, and so doing it this way, you get 2 different values. Let's see here. For the positive one, so for this one right here, you're going to get, and I'm going to round to the nearest tenth, 2.4. And then for the second one, you're going to get negative, and rounding to the nearest tenth, you get 0.4. And actually, on this particular one, I prefer that we don't round at this particular point because these are actually answers that we're going to have to plug into the original function. So I'm going to kind of renege on what I've told you there. Whatever your calculator gives you, write all the decimals out because you're going to have to take this and we're going to have to plug it back into the original function. It's okay to round our final answer, but it's not good to round something that needs to be plugged in. So this one we're going to write as 2.414. 21356.2, and then this one we're going to write as negative 0.4142135.624. All right, the other thing we need to do is make sure that both of these critical numbers are in the open interval. So they gave us the closed interval from 1 to 5. So if we come down to check, we're going to say, hey, notice that my first one is an element of the open interval from 1 to 5. So we're good to go on that one. But we notice this one is actually not because it's a negative number. So it's not in the open interval from 1 to 5. So that one's going to be out. All right, so now what we're going to do as our last step is evaluate our original function at the 2 endpoints and then also at the critical number that was in the region. And so on here, let me go back up and number right quick. So this was step number 1, finding critical numbers. All right, and then step number 2 was to go back and to say, go through and evaluate at the critical numbers. So that will be what I do here. So f of, and we're going to start actually with the endpoints. I'm going to evaluate first at 1. So f of 1. I'm going to just say at this point, do this on your calculator. On this particular one, if you evaluate the original function at 1, you're going to end up getting 0. Okay, then you're going to evaluate at the critical number. The critical number was the 2.4 whatever. We're going to have to use all those decimals. All right, evaluating there. This will be where I can do an estimate. You're going to get approximately 0.2071 and some more. And then also evaluate at the last endpoint. So the end point to the right was 5. Evaluate there, and you also get an approximate answer. You're going to get 0.1538 and some more. And then at this point, we want to evaluate the largest and the smallest. Okay, so here, as the third step, we're going to actually write our answer down. This will be the point where it's okay to actually round our answers. So we're going to say we have an absolute max of y equals, all right, what's the largest that we have? It looks like this value. So at this point, let's say round to the nearest tenth. So it'll be y equals 0.2 at x equals, and we're going to go ahead and round at this point as well. So if we round to the nearest tenth, it'd be 2.4. And then absolute min, looks like the smallest of the values is going to be 0. Okay, so we say y equals 0 at x equals 1. Okay, so we've got these as the answers here. All right. So finally, to end this section, what I want to do is look at a application problem so you can see the actual usage of this type of question. Okay, this one says for information given in a recent business publication, we constructed a mathematical model, and they gave it to us, and we noticed also in a closed interval from 30 to 65. And this model represents the miles per gallon used by a certain car at a speed of X miles per hour. It says find the absolute max and the absolute min miles per gallon. So sometimes what we do is when we try to go sell a car, we say, hey, this car gets up to this particular gas mileage, so that would be our absolute max. We probably aren't going to brag about the minimum. So, you know, if we know that a car could have a minimum amount of gas mileage, we probably aren't going to brag on that if we're trying to sell the car. But, I mean, it's information that we need to know. So on here, first thing, find the derivative of that function. So we're going to say m prime of x. On this one, we'd multiply the 2 to the front. What I'm going to do is multiply the 2 by the 1 that's already in the numerator. So it'd be negative 2 over 45, and then x. And then derivative of 2x is just going to be 2. So there, it's a fairly simple derivative. All right. And then from here, I want to find the critical numbers. So we're going to say critical numbers would be where the derivative is either 0 or where the derivative is undefined. This is actually a polynomial function, even though we have that fraction negative 2 over 45 in the front. The x is to a nice pretty power, so this is out. So we're basically just setting the negative 2 over 45x plus 2 equal to 0 and solving that. All right, on there I'm going to subtract over the 2. So negative 2 over 45x equals negative 2. And then what I'm going to do is multiply both sides by the reciprocal of this fraction here. So it would be 45 over negative 2, 45 over negative 2. And then that way this all cancels. That leaves me with just x. Over here, the negative 2's would cancel. That leaves me with 45. So 45 is my critical number. Now, I need to make sure that that's in my region. So notice here that X is representing miles per hour. We're saying we're going to have a minimum mile per hour that we're going to talk about for this application of 30, a maximum of 65. We notice this is in the open interval from 30 to 65, so that's going to be something we can consider. So number one, we've found the critical number within the open interval. Number two, we're now going to evaluate this function at that critical number as well as the endpoints. And once again, I'm just going to do this on the calculator. At this point, I'm not going to show a whole lot of work. This is okay for you to do on a test. I understand at this point you're using a calculator. So you tell me m of 30, and then just tell me the answer for that. Evaluating that on the calculator, you get 20. M of my critical number, 45. Evaluating that back into the original function on my calculator, I get 25. And then m of, if I go up to 65, which is the endpoint, from there I'm going to get a decimal. That's 16.11. I think that's repeating. So on that particular one, we can see that our high occurs when we're going 45 miles per hour, and it looks like our low occurs when we're going 65. All right, and then here on our last step, we need to state our final answer. We're going to have an absolute max of, and in this case, what I'll do is I'll state this in words as opposed to a y equals and an x equal. So we're going to say we have an absolute max of 25 miles per gallon when we go 45 miles per hour, or you could say at a speed of 45 miles per hour. And then also we have an absolute minimum of 16 point, if we want to say 1 repeating, miles per gallon at a speed of, and that was 65 miles per hour. All right. Let me know if you have any kind of questions.